Thank you so much. Really appreciate it. Thanks for you all for coming. Thanks for inviting me. It's my first time visiting your campus. It's gorgeous. I was really excited to have the opportunity to come. And sort of my history, I've been at UC Santa Barbara about 10 years. Kind of worked through the ranks of programming language and compilers, moving through, sort of expanding to other more modern languages like Python and Ruby, and then sort of how we can interface and make those high-level languages as easy-to-use languages available to all kinds of researchers, scientists, and electrical engineers who want to bring to bear larger and larger scale to their computing problems. And so with that, we have recently been working on app scale, and that's what I'll talk about today. So cloud computing, just in general, to make sure we're sort of all on the same page, is really an evolution of a lot of great work in computer science, and it's a combination of grid and cluster computing and elastic computing, distributed systems, and it's sort of like the perfect storm. It exists today not because it's new and novel, it's just because everything came together. We have the virtualization technology in our hardware and our software now. We have all of this great work from the past distributed systems that we can bring to bear, and actually now there's actually market models. There's economic models for business models for actually making money using cloud computing. So the combination of all that has made it sort of exciting and popular as it is today. But it's really a culmination of what came before. The idea here is that the cloud computing is the idea where you want to access large-scale, vast resources for storage and CPU and memory and networking remotely through well-defined, high-level interfaces via the web. Right? So everything is kind of interconnected. And the idea is you have companies who own these large-scale clusters, huge clusters, Google and Amazon and Microsoft and IBM. And they are using those clusters, but not all the time. And they want to give you cycles on those clusters, allow you to use those clusters and automatically scale elasticity. So give elasticity. So they automatically let you grow and shrink your problem according to the resources that are available and according to what your problem needs. And you pay per use. You rent a tiny little piece of these systems. So you have these vast, cluster systems. This is a picture of some of the, what we think, Google's sites near water, good, for power and energy. And then you rent a small fraction of these. But the key is that these are opaque. You don't know what you're getting. This is not scientific computing. Not where I know what machine I'm going to. I'm going to highly customize that. I'm going to have special compilers and all that. No, that's not it at all. You don't even know what kind of machine you're going to get. You can say, I want this many processors. I want this much memory. I want this much storage. And the technology that's underneath is whatever you get. So it's opaque. So it's very different. If you want to do high performance in that space, that makes that challenging. It's also isolated. You can have multiple virtual machines, multiple full systems, and running on the same physical hardware now. And you and I could have our jobs running on the same physical hardware, sharing those resources, but they're completely isolated from themselves. So the underlying software technology to enable this is quite complex and interesting and advanced. I'd argue that there are 3 types of cloud computing, and people do argue with me on this, but I like to break it up into pieces so you can kind of see where I fit. At the very bottom, I think of it as like the operating system for the cloud. You have the infrastructure layer, infrastructure as a service. And what this is where companies like Amazon and Rackspace give you access to entire operating system images. You have an operating system, you have your applications, you customize it. It's completely self-service. You take an image, you make it into the system that you want, you configure everything, right? You have full power, and then you deploy it on these physical resources. Fully customer self-service. Full runtime stack, you get root access. So I see that sort of as the operating system for the cloud. The next layer, the runtime for the cloud. This is a platform layer, and the idea here is that a company, instead of giving you a cluster of virtualized systems, what they're going to give you instead is a huge cluster, and they all are running this platform, this runtime system. And that runtime system implements a set of APIs. Those APIs are for database, very scalable and highly available databases. Those APIs are to use authentication, to use the user database to have your users use your applications. It has messaging and mail and all the services that an application would need. And they're all accessible through an API. And so all you do is code in different languages, .NET languages like C#, or for Google it's Python and Java. And you code and you write code against these APIs. And then when you upload your code to these platforms, what you get is that those APIs are implemented in the background with proprietary implementations that are very scalable and very high performance. So you get an entire software stacks that you then write your code against, and you upload your code, and that code executes against these APIs. It's isolation at the process level, whereas here we had complete isolation of your virtual machine. So even the network is isolated in a system like Amazon's, and so that's why it can control what you use, and so but also that that way you can be paid for, charged for what you use, and then you're independent of everybody else that's executing. At the platform level, we're giving you process level isolation. So you have one machine, one system, one operating system, and lots of runtimes are running at the same time, yours and mine. If I have a denial of service attack, or I load the system down, I can affect your program, your performance. It's not full isolation, but it's safe, right? I can't get to your code or your data, but I can affect your performance. Isolation. But starting and stopping things is really quick. How many of you have ever used Amazon's EC2 system? Okay. When you start a VM in EC2, it takes a while, right? The bigger the VM, the longer it takes to get started, right? These are little processes, really lightning fast to get started. So if you want to grow and shrink, EC2 is going to have a harder time getting things going for you. You want a whole nother operating system instance, that operating system has to come up. And those operating systems are disk images. They have to move across the network, across the disk. That is minutes, right? On the order of 10, 15, 20 minutes to get Amazon instance up. At a process, it's microseconds. And so you can grow and shrink much quicker. You're much more agile. So just kind of comparing and contrasting here. And at the very top, there is applications as a service, or software as a service, SaaS. And here the idea is, from a commercial perspective, is that what the company will do is they'll write a program and they'll deploy it on the web. And then you will pay them to have an instance of that program, and you can customize it however you want. So Salesforce.com is an example of this. Note, you don't run any code. You're just kind of configuring the application that they wrote on their systems to your needs, to fit your needs. Okay, so that's great, right? Lots of really cool technologies in action. We have lots of access. And the idea here is, instead of you managing your own cluster, you managing your own compute resources, that costs money. You got to buy them up front. You got to turn them over. They don't live very long anymore. Sure, the cost is low, but you got to turn them over. They're hard to maintain. You got to pay someone. You have to have a system administrator. If you configure them wrong, you're going to have terrible performance, right? You got to pay someone well. Right? Someone who knows what they're doing. So the idea here is, why don't we just pay someone else to do that? I just want someone to configure my cluster. I just don't want to manage it. I don't want to buy it. I don't want to know about it. I just want to run my programs on it. And that's really the idea of the cloud. So that's why business has found this really appealing. There is a commercial component to this, because people will pay for that. And it actually turns out to be less than employing a system administrator per year, depending on your use cases, than if you owned your own cluster. And so that's really the trade-off that companies are experiencing. And if you look at who's using this kind of thing, a lot of startup companies. You don't need to do that initial investment initially when you're starting your company. You can use other people's technologies, and then later maybe get your own. But there are some downsides. First of all, this is great, right, for Amazon and Google and Microsoft and IBM. But a lot of these things, this kind of automatic growing and shrinking, this ease of use, this using cluster systems automatically across the network without kind of knowing what's going on, that's appealing, right? I want that for my cluster that I have in my machine room at UC Santa Barbara. I want that technology. The things that work in the public are also really useful on premise. Right? So we want that technology on all clusters. Another problem here is that, and this is a pretty important one, the idea of vendor lock-in or non-standard APIs. If you use Amazon, they have a set of APIs. If you use Google, they have a set of APIs. If you use, Rackspace, they have APIs. If you use OpenStack, they have APIs. Right? They're all different. Which one are you going to code to? You code to one, and now you change your mind, or the price goes down on the other guy, you're stuck, right? It's really hard to re-engineer your code to go and use some other set of APIs. They do the same thing, however. They're doing the same thing. They have database services and email services and accounting services and business services. But they have all different APIs into the same services. So you're going to have lock-in. You're going to have to code against these APIs. And you, the individual who's using these systems or these applications, has to change it. The other problem is it would be cool. So you're paying some. You're paying for these public resources. But all of us have some cluster sitting around. It'd be cool if we could use that cluster initially and only go out and pay for it when you really needed it. When you're running that job for that paper that's due tomorrow, right? When you need all those cycles and you need to run 10,000 jobs. So you pay, at 25 cents and you get that extra speed or you get that extra scale. Right? You want to do that in a hybrid way. I would argue that we'd want to use it locally and then fall out to the cloud when you needed it, public cloud. The other downside of the cloud is that you're putting all your stuff up there. Say you're starting a company, brand new great idea, starting a company, got a couple of buddies you're working with on this, got your first round of funding. Now you're going to put all your proprietary information, all those new ideas, all that data, all that custom information on somebody else's machines. People are really scared of this. And there's a lot of great security work being done to help ease this fear, but this will be a fear, and this is going to be a problem because people just can't get used to the idea that, and Amazon promises it'll be okay, and Google promises it'll be okay, Microsoft promises it'll be okay. Do we trust them? What happens when the government goes to them in some horrible situation and says, "I need this information," That information is now no longer yours. So people are really scared of this. So I'd argue that we'd also want to have some local cloud support, private cloud or on-premise cloud support in order to kind of calm some of these fears. I'd also argue that, I'm not sure how you guys develop code, but I develop code with a mental model of where it's going to be executing, right? If I'm just going to throw it out there on the cloud, I can't kind of understand what that's going to be. I can't develop my mental model. I'd like to develop locally, test it out, get my head around it, code it correctly. It takes a while. It takes a few iterations to get my head in there, and then I can deploy it. And so it'd be nice if we had the same sort of cloud technologies locally, and then we could go to the big stuff when we needed it. I also am a big fan of optimizing code, making it run really fast on the resources you got. But if you run your stuff on clouds that are public, sure, they'll tell you how much they're going to charge you. They'll tell you how many CPU cycles you're going to use. But how do you know what your program's doing? Is it really running? Is it running correctly? How are you going to debug this? How do you know that it's actually, configured correctly or optimized in the best way? Google doesn't care. If your program runs slower, they're just going to charge you more. Right? So there's no incentive for these guys to give you all this sort of information. So there's an opportunity, I think, for research. And lastly, web services is the name of the game in clouds, right? If you're going to have a company, you have a web interface with a database backend and some intelligence in between, that's what everybody believes that clouds are good for. Because there's money in that. There's a lot of companies who can start a company real quickly, startup company then real quickly, because all you really need is a web interface and some way to get your customers to give you a credit card number. However, we've been doing a lot of work in grid computing and scientific computing and high-performance computing, and this is exactly what we want. We want to not understand those machines. We want lots and lots of scale and high performance. We want to write in high-level languages. We want it to be really easy, and we want it to run really fast. So, the potential of the clouds and the super scalability that it offers, lots of processors, lots of memory. Who's going to go out and buy a big memory machine? I can't afford it. Not on NSF money. So what I'm arguing is that, well, it's great for web services and it's optimized for web services. What would we need to do to change it to make it run for these other domains that we could really have an impact on the world with, right? We could forward science, we could improve medicine, we could do all these great, great problems and simulations that we need to do to understand at super large scales. All right, so that's where, that's our motivation. And so what we decided at UCSB, this started with a project with Dr. Rich Wolski at UCSB. He's more of a high-performance computing / systems guy, and it was really his idea to bring on-premise, popular cloud, popular public cloud support and interfaces and APIs to your local clusters. Make them open source. Make them available for your local resources, and bring all these great cloud fabrics to your own clusters. And you're going to emulate what's happening out there in the real world. The idea is we can engender the user community that's already there. There's lots of users, there's lots of apps, right? Sure, they're web services, but that's a great place to start. We can understand what clouds are doing. We can understand what the next generation of cloud computing might be like, distributed computing, right? So we want to bring things that are working and that exist to your local cluster, to on-premise clusters, to your private cluster, make them private clouds, and then we want to expand on them to do interesting things, to understand and do interesting things. So at the 2 levels, we had 3 levels when we started. It was infrastructure, platform, and software as a service. Dr. Rich Wolski has worked on Eucalyptus, and that is an open source implementation of the Amazon Web Services. It works on your local cluster. It is open source. It is free. Works great. He spun off a company just because his open source community was so humongous that in order to support them, he actually needed to have a company to do that, employ programmers to help with that. So he's working on that. I took the same idea and said, well, I'm a runtime systems person. I come from Java virtual machine land. I want to write a Java virtual machine for the cloud. Write once, run anywhere. What a great vision, right? And so how are we going to start there? How are we going to start that? How are we going to get moving on that research agenda? Well, what we can do is take an API like Rich did with Eucalyptus. I chose Google App Engine because the only other option was Microsoft Azure, and it didn't exist when I started this 2.5 years ago. There was a lot of talk about it. I knew a lot of internal stuff because my advisor worked up there, but it wasn't real. And so I took the Google App Engine APIs, and my students then provided implementations of them. And I'll talk a little bit more about that. But the idea is now you have a platform and an infrastructure that mirrors what's out there in industry, so you can experiment with and understand. You have an automatic transfer path. Right? You use it locally, it's going to work out there. It works transparently. Any Google App Engine application that runs on my stuff runs in Google, and vice versa. So when I'm ready, I move out to Google. When you're ready with your images, you just move them out to Amazon, and you can move them back and forth. And so that's our research agenda. That's where we started. So any questions on that? You want to talk about anything so far? Yeah. Well, I will never replace Google. Google has, really, virtually unlimited resources, infinite resources, I'd argue. I have a cluster of 12 now with four cores each. I may someday have a cluster of 24, right? And I have to replace those. I'm never going to have that scale. So I want to work on bigger problems than that. I want to solve harder problems, right? Your machine learning stuff, computationally driven. Let's run it locally, get it all going. Yeah, that'd be fine. But what happens with the Oak Ridge and the grid community, sort of the HPC community, is that the idea is you are using in isolation by itself a group of resources, right? You have full control, and that's fine if you want to control it. But if you want it to be shared, partitioned across lots and lots of users, that's where you get your scale. And so to have super scale, then I would say what we want is we want to use those resources if they're available to me. But again, there's a middle ground here. I think you can use your local resources and spill out, solve your problems as you need to on the fly. And then for very particular applications that work really well for this dedicated use model, then things like the TerraGrid are perfect. Right? But we need something in the middle, something that's easier to use. And that's really the motivation for me, in my opinion. Other questions? Yes. Are you asking if the intent is to deploy on my stuff first and then Google? The intent is that's one way to use it. If you don't need super scale, then you could just use your local cluster and never have to pay. And really the intent is to provide a platform for users to experiment with what's next, right? Not just web service. So now you can get in there and modify. It's all open source. So you can figure out sort of, what database technologies we want, what kind of high performance computing support we want in there. So it's a research infrastructure, yeah.
So how do you know that? So Google is many times bigger than
M-
infrastructure, right?
yes,
How do you know even if your code is running perfectly well on your own cluster,
yes.
with that many times bigger infrastructure of Google, like you have code the code there, whether it is on there. So in other words, is there a way of showing that okay that your infrastructure defines your infrastructure or something like that?
Well, the functionality is emulated, so we can only infer because it's proprietary what they're doing, but it's transparent. So there's no porting. You mentioned porting, no porting. You have an app.
Code has to move, right? Code has to go to
Yes, and so we as the researchers or as the open source provider provide you with those tools. Yes, yes. Have you heard of RightScale for Amazon?
my question is not about the code.
Oh, okay.
Is
Who does the actual physical falling out? Okay, okay.
my question is that suppose your code is running perfectly well
Yes,
on your own cluster.
yes.
Suppose after the code is taken to Google, like what makes you think that it will still run correctly, given that Google's resources, Google's cluster is many times bigger than this?
I see. Well, we have to discuss what you mean by correctness then, correctly, right? And so if, for example, you're talking about sort of precision in terms of your computations, then it does matter what the architecture is in some cases. For those applications, I think, that are so specific, specialized hardware might be fine. What I think is that, it will still run the same way because we're just implementing the same set of APIs. If it's running perfectly, it won't spill out. You don't need to. But this is a cloud. This is not a runtime for one application. It's a runtime for lots of applications. Let's say lots more applications come along. There's another professor in the department who has a paper deadline who's using the same resources. Now, you are not getting all of the resources that you had before, so you need a few more. So you're willing to pay a little to make your deadline. And so this is really a sharing of resource platform. Yes. Did you have a comment? Rama? Yes. So the characteristics that we've been looking at are like availability, the resource availability. It actually turns out that Google can offer higher availability just because they have more redundancy. And so if you need super high, redundancy, then you could also just go directly to Google or have some subset, have your data in Google. Consistency guarantees are the same, strongly consistent, eventually consistent if you're using Amazon. If you want that, you have that access with us as well. And then just API functionality. It's just functional specifications at that point. So beyond that, I haven't thought of it. Yeah, that's really interesting. So we're working on that right now. So the idea is, growing and shrinking, you could easily, that's really hard. It actually is a really hard scheduling problem. And you don't want to thrash. You want to grow and shrink, and you don't want to fall out and all that. So, no, that's in research. I don't know. I don't know the answer to that. It depends on the application for sure. We start with simpler applications. Scientific, highly, embarrassingly parallel guys. So whatever I get, is the more the better. Yeah. Yes, I would say that if they allowed, their API to grow to encompass some of these public cloud APIs, so that there would be a better transition, say from Google to Nimbus. I would argue today that is impossible. Impossible. I mean, but they do the same thing. They have the same back-end support. And so what I'm trying to do with this platform is my platform can run on anything. So that's more of an infrastructure, I'd argue. And what I can do is I can provide that for you. I provide the Google and the Amazon, any API that you want, and then I can implement it with Nimbus or with Eucalyptus or with OpenStack or with Amazon, right? And so I want to provide a software layer that makes that transparent, that tries to abstract away all of those APIs. That's really what I'd like to do. Have the platform do that for you. Go ahead and build your infrastructure as you think is best with your APIs. You talk to me. I help integrate those into the platform, and then people can just use them directly without touching their code. That would be where we want to go. Yeah. Yes. and all your data. Yes. Or Microsoft or Amazon. Well, the people that I've talked to, I have a lot of people that come and talk about this because they're all curious where the platform is going to go, business-wise and research. And a lot of people want a backup of some sort, a hot, what's it called, emergency response, sort of disaster recovery. And they want it. And what they want to do is they think that what you could do is you could partition your data so that looking at some individual subset doesn't give you the whole picture, but then you're in different clouds, which are different domains, and so the government will get everybody, and that's very unlikely. So you just want to reduce the likelihood that someone could get information, and then of course just really cool, privacy and security techniques you can bring to bear on that. But like let's say. JPL, for example. I work with JPL, and they are interested in having a large subset of their data locally. They have large-scale storage systems, but they want to operate in Amazon sometimes. We can do all kinds of encryption mechanisms, but we can just do some computations locally and see when you need to actually move the data, and then make a policy decision on whether that's the data you want to move or not. And they do it on a case-by-case basis, and this just gives you the freedom to do that choice. And I think also people will get more comfortable, right? We are getting more comfortable with letting our information out, and that'll happen over time. And I think this will actually encourage it. I'm not against it. I'm just saying this is what people tell me. It's like we need this because I'm scared to death of putting my stuff out there. No, and in 5 years, those same people, if it's really cost effective or if it really forwards science, will start to do that. And we'll either have to come up with mechanisms to protect them, or they'll just be more comfortable and we don't have to worry as much. So it'll be interesting to see. But I think this will spur that question and encourage people more. That's what I tell the big companies when I go ask for money anyway. Other questions on this? Okay, I just want to give you a feel of what AppScale does. Anybody out in here used AppScale before? Google App Engine, I'm sorry. Anybody in here ever used Google App Engine? Okay, so the idea here is that you write a Java, sort of application or a Python application, and you code against a set of APIs, users, instant messaging, big large-scale storage, individual background tasks. You can do MapReduce for this kind of thing now. Memcache, so local computation, local data caching. Cron jobs that can fire off tasks in the back, mail, images. And then the big one, of course, is Google's Bigtable, Megastore. And Megastore is a software system on top of Bigtable. And the idea is all these things that you have access to have a set of APIs. You take these APIs, you write your code against them. Google defines them. And then they give you an SDK. Download an open source SDK to your machine, and you can run your program over this SDK to test it and to develop your indexes for your database. These SDK, just for each of these interfaces, either isn't implemented, it's just a stub, or it's a really slow, dumb version, serial version for your local machine. It's just an effort to let you your bugs serially, no distribution now, no scale, and before you upload your code to Google. Once you do this, so what we did is, let's see what's next. Okay, so once you do this, then there's a bunch of restrictions that Google places on you. Don't expect to do anything very large scale or very long running or very computationally intensive or very high throughput, because Google really restricts you down. It restricts you down into the number of things you can call, number of processes you can handle, number of requests you can handle at a time, how much CPU you use, how many system calls you make. You can't do anything to the underlying machine. Very restricted, right? It's fun, but I would argue that it's still in its infancy stage, right? You can't do a whole lot. I would not run my business on it. Google's figuring out, is it going to be something that you can run your business on? So another thing that what we'll do by implementing this in open source is we don't have any of these restrictions. You don't have to worry. And what's interesting about this is Google restricts you so that they can enable scale. If I stop restricting you, what scale can I ensure? What can I get out of your cluster resources? And that is the research question. I don't have the answer for that, but that is what I'm interested in, those kind of questions. When you upload your code then that you coded and you tested with your SDK up to Google, it uses the local resources for nothing. It's free, right? And so you can have these large-scale, web services with those restrictions operate in Google, and then Google will grow it and shrink it for you. Okay, and you can access it all and see how it's all running from an administrator console. So what we did is we took all that SDK with all those APIs implemented via stubs, and we just cut off all the stubs. And we implemented with our own highly scalable, highly available open source implementations. And we did not reinvent the wheel. We used open source technologies, if we could, that were available. For the data store, is the big one, because that's where most of the performance goes. It's a pluggable, database agnostic interface. We're able to plug in all kinds of different databases. These are the ones that we've got now: Hypertable, HBase, Cassandra, Voldemort, Mongo, Memcache, MySQL, Oracle. Well, I can't ship Oracle because of their license. We have Memcached for the Memcache API. Both for Python and Java, works great. We implement our own tasks interface, but allow you to use Hadoop in the background to write mappers and reducers in any language and spawn them off, so we can grow and shrink your MapReduce jobs in the background based on your data. Cron jobs is just the Linux cron interface. Users, this goes to Google users, so all of the Gmail accounts, and the mail goes to Gmail. So we had to build our own authentication system and user database, but this again is pluggable. So, like for example, Oracle is really interested in taking this and using this for their platform, and they said, well, we don't want your authentication, we want to plug it into ours. Fine, it's just an API. It's just like 4 or 5 calls, really. Here's what you need to do, and so all these APIs you could implement any way you want. All right, so it's a full-scale distributed system. If you look around, and there's a lot of other Google App Engine SDKs out there, right? That software development kit that are serial and operate on one machine, and they're lightning fast. But this is a full-scale distributed system. And again, and it's just the Google App Engine APIs, and then we added some APIs, and are going to evolve that over time. We started with Google, again, to engender the Google users, to get a bunch of users on our open source platform, and to get their applications. If you work in software or optimization performance, what's really hard is how are you going to measure performance, right? You have a set of benchmarks that nobody believes. And in fact, if you believe them and you run them on real codes, what you'll find is that it doesn't work the same. Maybe better, maybe worse, but it's not the same. Benchmarking is really hard to do. Getting the right applications. What happens in the real world is very different from what your benchmarks do. And so I really wanted, and in programming languages is a huge problem. So what I really wanted was real applications. I wanted system that I could just take things that people would run on Google App Engine and run it on my stuff, so I could watch and see what it does and what people want to do with it, and that's something that this offers you. The databases are let's see what I want to say here. Distributed, highly available, redundant. You can have strong consistency or eventual consistency. Nobody wants eventual consistency that I've talked to, so we pretty much turn that off. It's an option, though, for the database that supports it. Put a transaction layer over the databases. We have application servers that grow and shrink. This is the front end, the server that manages your website. And then we have a load balancer that takes care of the load throughout the system. That's right. So I don't. But it's called configurable. It is possible to provide some combination of those that you choose, except for not all 3. Exactly right. Exactly right. So our transaction layer requires that you're using the strongly consistent implementation for the databases. That's right. And you get to choose. You choose, and it can be on a per application basis. Right, which is what I was really most interested in. When can you tolerate eventual consistency? Does eventual consistency really give you that much scale? When? Right? Google and Amazon and with Dynamo is out there arguing that, oh, it's so much more scalable. It's so much more scalable. Sure, if you have 10 million processors, but I have 42, right? Do I get more scale, right? What does it look like for you? What does it look like for your application, right? I think that's really interesting. I don't know the answer to that. That's why this is interesting to me, because then we can use a platform to figure that out, right? Use it when you need it. And you don't have to be the be-all, end-all for every application. Customize it for your application. So the API for the store is just this abstraction layer for these databases, and then we plug in these databases. And a lot of these databases are most of these databases are key value stores. Did I give you a list of them? Here they are. Tell me what? Yeah, my transaction support and my locks are via Zookeeper. Yep. And we just have our little configuration of using that, and that gives us our consistency. I mean, our locking across the system, distributed locking. Slower. I have data to show you. I don't have data here, but I can give you a paper on data that shows you the difference of when you have transactions turned on and when you don't. Again, customize. If you're not going to use transactions, do not take the hit. Right? If you are, then you need to take the hit, right? Maybe you need some of your application using transactions, some of them you don't, right? It's a huge performance hit in a distributed environment, unless you have a specialized database and machine. So, but you can choose. You get to choose. And that's what I think is interesting here. Mix it up, adapt, figure it out. These are the databases that we offer, and really why we chose so many. Once we could do a couple, then it's pretty easy to plug these things in. But they're all different, right? Some of them are different languages, Python, Java, C++. Some of them are peer-to-peer. Some of them are master-slave. Some of them have relational support. And I'm not a database person. I like to look at this from a systems perspective. You know, how is this using the underlying resources? How is this using the disk? Could we adapt, right? Do the applications need all of this, right? They're heated wars out in the ethos about which one of these is best and why this is so much better than that, and it's really cool to kind of figure it out for yourself and what the right answer is for you. The load balancer Ruby on Rails application, plus a couple other layers just to try to make it as distributed as possible. You can place anything anywhere. You can put database masters and slaves together or not. You can put that load balancer someplace. You are in complete control of the configuration. What configuration is right? Depends on the system. Depends on what you're running. How many applications, right? Tons of research questions here. All for the taking, right? There's no way we can answer all of them. And so I'm hoping this platform will allow people who are interested in sort of distributed systems or these high-level languages. How does Python affect you? How does Java affect you? You know, they're very different languages. Maybe it doesn't matter, right? There's flame wars about those, right? But in some cases, it really doesn't. And the programmer productivity you get from these high-level languages actually makes a huge difference in who writes code for your system. So there's a really interesting, sort of challenge there too. Did you know another point? The load balancer also has a full monitoring. I'm a big profile person. I come from a profile guided, feedback directed optimization background. That was my thesis. I love that stuff. And I want to do it at the big scale. So we profile everything. You name it, we profile it. We can turn it off too because that's a lot of overhead, I know. But it's really cool because you have all that information. And you can kind of see what runs when, maybe, because again, the whole holy grail for profiling is you don't want to profile much. You want to just kind of take a peek and sample, but you want to have the full answer. You want to know the complete behavior by just taking a peek at these things, right? That's the holy grail. So, so that's nice. There's good challenges here. What happens if we just looked at how that API was being crossed, perhaps? What happens if we just look at how the service is being used? Maybe that tells you what the program is doing, right? There's all kinds of really interesting profiling techniques that we could investigate with this. Python and Java work right now. The Java is kind of interesting. I'll tell you this as a story just because you might find it interesting. Python's open source. I mean, it's available, right? You get the Python code, it's Python source. So you could distribute Python bytecode, but people don't. Java, however, is, because it has such a long and storied history, Google's lawyers decided that they would release the bytecode to us for their SDK. Notice we rely on the SDK. We take the SDK, we chop it in half, and we put it in our stuff, right? So we have the Python one and we have the Java one. Python one's easy. It's all Python source. Java one's bytecode. And I've been begging them, and they're on my side. They've been trying to help us all along, but no, the lawyers will not give us Java source. So this turns out to be an immense pain. Big portion of our engineering overhead went to this. You have to decompile all of the Java stuff. You got to figure out what decompiled parts don't work and fix them. You got to go in and find those APIs, which are now decompiled, and there's no comments, there's no names. A function is called A. Great. How are you supposed to figure out what that's doing? It was such a bear. So I would say that our implementation of the Java side is kind of weak. So I think it's a really interesting opportunity for people interested in sort of Java runtimes to figure out what sort of this interface needs to look like, because Google's not going to give it to us. So we're thinking, if you've heard of Amazon's Elastic Beanstalk, it's a Java container solution for Amazon. We're thinking of doing something along those lines as an interface to AppScale. But it won't be AppScale, App Engine compliant. It works now in this release what we're going to put out in the next couple weeks. It'll be supported, but I don't think we're going to support it after this. It's just such a bear until they give me the source. So it's been fun. In the very beginning they did, and after that they're like, no, you're doing great. I'm not going to. And in the beginning it wasn't much. So Google's very tight with that kind of thing. And they don't know where they want to position themselves, right? They either want to hire my whole group, or they want to wait for us to start a company and then acquire us, or they want us to just do all the work and then they'll take it. It's open source, or they'll do it themselves. And they haven't decided what direction they're going to go. They have said that they're not going to shut us down, right? That we are. They have given us permission to go forward with this. So we'll see. I send students there. They don't know where they're going with Google App Engine. They're trying to figure it out right now, right? Where's the business model? They're business driven, right? They're money driven. So we got to figure out what the business model for them is if we really want this to go. I'm not tied to that, so I get to kind of play around and figure out what the next generation should look like. We have all kinds of non-GAE compliant, non-Google App Engine compliant APIs. Because right now, I remember I started my story with there's all these different APIs, and I've chosen one. Right? I haven't solved the problem. We have to support lots of APIs. And so what we do is we have this platform, and it supports a lot of infrastructure APIs, Eucalyptus, Amazon, we're working on Rackspace and OpenStack. But we also want application level APIs. So we have MPI, HPC. You can use the X10 language if you've ever heard of that. It's a concurrent language. We have I have a student working on streaming support for the cloud using this kind of thing. So this is where we'll go and grow and develop. Again, runs over Eucalyptus, Amazon's EC2, Zen, and KVM. That's in our release. And we do all kinds of things internally. I'm happy to give away anything that we do if you're interested in any of this. A lot of interlanguage stuff. You got to communicate between languages via Thrift, and you have to have some sort of data serialization. We use protocol buffers. But students that are interested in sort of language technologies and language interoperability could use this to find new ways to optimize across languages. No one's really looking at that. I really think that's a nice problem. We looked at how to do shared memory support across languages. That's a really cool problem. Lots of interesting research to do there. The one thing that AppScale gives you, it allows you to compare and contrast the different services. So this is just a graph of the different services for the databases. This is a heavy load. I'm just hammering the system. It's just round trip time, and this is with transactions. So and what you can see is you can't take away the actual numbers themselves don't mean a whole lot, but the relative difference between the different colored bars does. The blue bar is Cassandra, the yellow bar is Hypertable, black bar is MySQL, green bar is HBase, and these things are in flux. And all of these guys work with us because they know we're going to put out these numbers. And so Hypertable, is where's my Hypertable guy? Yellow, and they've been working with us all the time because they're not doing so well. So we work with them all the time. So the students have a really good opportunity to work with these guys. It's really fun. Cassandra was way up here before. Now Cassandra's the best. MySQL is interesting. MySQL has its own transactions built in. So what we're comparing here is the transaction overhead of MySQL with built-in transactions versus our system-wide transactions, our distributed transactions. So this is quite an interesting result. No. Okay, let me explain that. That's a great question. Thank you. What we've done is we've used this API to the data store, and the API is a put-get interface. It's put, get, delete, and query. Okay, that is the API. We implement that API with these different databases. So MySQL, we're using it like a key value store. We have put, we implement, and get, and then we convert the queries to SQL queries. Okay, so it's very simple in terms of how you use these databases. I can't use all of MySQL. I could let you. But right here, all we're doing, it is apples to apples because this is what the application perceives. What's under the covers, it doesn't care, right? And that was the goal. What else do I have? I have throughput, just to show that as we add more and more machines, you get more and more transactions through the system, and in this case, again, Cassandra and MySQL are the best. But again, this varies, from release to release. That's why it's so important to have something like this, because Cassandra comes out with something. You've been using it all along, saying, "Oh, this is the best," or "This is what your baseline is." Cassandra comes out with a new version. That baseline changes, right? All you have to do is download our stuff. We will support it, right? It'll just plug in, and I think that relieves researchers of this burden of configuring and deploying and try installing even a MySQL server. It is a MySQL cluster. It is a huge pain to get that configuration right, and we are experts at it, so to speak. And so it takes us a long time. It's going to take to the average user an immensely long time. It's a complete waste. Why should you have to configure MySQL? Why should you have to configure Cassandra? How about you just download AppScale and have them both can be configured for you, right? Saves everybody all this time. And so that's a service we want to provide to the community. If you want to compare it to Google, it's kind of hard to compare to Google. We are on par with Google. Here's Google App Engine here. This is MySQL, so Cassandra does actually a little bit better. That's the only numbers I could grab when I was flying out here. And so the actual transactions for put, get, and delete are the same. Again, we don't know how many nodes we get with Google. They just give us nodes because it's opaque, right? We know how many nodes we got here. And then a query, we actually do better, but this is... yeah, and so our query just happened to do better for the SQL stuff. And so this is just for raw operations. With Google and with any public cloud, you're going from your machine to Google or to Amazon. You need to remember this, because that's latency. That's a round trip time. To go into your local cluster, if you have a big fat link down to your machine room, you don't have that latency. So we also have almost an advantage in terms of performance, not scale, right? Because I can only scale to whatever you give me. But performance, because I don't have that round trip time getting to the machines that are in, New York, or the machines that are in Idaho, right? I don't have to go that round trip time. So if you're really latency sensitive, so a lot of my scientific computing people are pretty excited about this. Oh, I can use my local cluster and get that scale and performance, and I don't have to go across a huge link and the internet to do these operations. All right, so that's pretty much it. We do release. We wanted an open source experience. I'd never done this before, and I wanted to try something new, and I wanted to see what it was like to support a community, and that's where we're at. It's a lot of engineering, took a lot of time, but it also gives us a lot of experience with which now we can start to ask about research questions, right? So I made a conscious decision with my students who chose to be on this project. They knew it was going to be a lot of engineering and that the research would come later, and now the research is coming. But some students, they just wanted to focus on research, and so it's really important to see that there's a difference there. And then I give you all kinds of research that you could do. There's all kinds of interesting things. The scaling's the hard part. We're working on that now. Trying to get interesting HPC kernels as a service into our system is what we're working on now. Data analytics support, large-scale, data processing. How are we going to get that into the platform? This is really interesting. Platform and infrastructure kind of coordination. If you think about the Java virtual machine and the operating system, they do a lot of the same things. So do the platform and the infrastructure. So maybe you would want to look at how to more tightly integrate those two to get some better performance. Because if you think about an operating system or an infrastructure for a cloud, they have no idea what's executing. An infrastructure just takes virtual machines and executes them. But what happens if the infrastructure knew it was MySQL running in that instance? What happens if it knew that it was a compute-intensive HPC kernel running in that instance? If it did, it could make better scheduling decisions, because you could make better scheduling decisions if you knew that. So the platform knows. It knows exactly what you're doing. Not even that it's database versus HPC, but it's how many requests per second, how many transactions, how many Python operations are being executed, right? It knows everything, fine grain. Is that useful? So I think those are going to be interesting questions. And so with that, I will leave it to give you some time to ask questions if you want. But I couldn't do it without my students. They are the engineers. They are bring a lot of the ideas to the table. I do have visitors as well. Yoshi Nomura from Fujitsu was with my group for a year. They're amazing, and I thank all my supporters as well, because I can't do this without funding. And again, it's a lot of engineering, so you've got to have people who are invested in that. And so I'm very grateful for that. So with that, I'll stop, and I'll leave it on the research question slide, and we can talk about ideas that you might have. Thanks. Okay, questions? Yes.
I have a question related to legacy codes.
Yes.
The U.S. Postal Service approach to
Yes.
and that we're re-implementing our backends. We've got a 25-year-old legacy system. We're implementing something that we want to last for another 25 years. We're basing it off Google, but we're not sure 25 years from now will they still be in the same business.
That's a great question.
2 years from now, can we begin investing in your effort
Yeah.
so that we can guarantee that whether Google's in it or not,
Yeah.
we'll be able to use this 25-year forward?
Yeah, I think that's a really great question. I think that, having a platform abstraction is one of the key pieces to enabling that vision. Whether we will be able to enable that or not, I don't know. But having that layer between, the actual implementations and how the users use it, the legacy codes, allows us to swap out that layer and the implementations and allow those legacy codes to still to execute. So I think, as soon as we start to build those abstractions, the better. Also, I think we have an opportunity here, just sort of on another sort of side research idea, is with virtualization. We are able to take snapshots of, execution environments, runtime systems, and as long as we can take these virtual machines, we could keep those forever. So now, instead of a legacy application, you have a legacy environment. You have all your libraries, and it runs, today, and we could keep those if we had some sort of archive for that. And as long as we had virtualization support, that's like another layer. We could always run those applications, right? We could, if we had no more source code even, we could always run those because we could keep those. A lot of people are talking, start to do that things, but we need to, put our money where our mouth is, and that really hasn't taken off. But I think that's a great question, and it's definitely something we want to work on.
Do you have a sense if Postal Service, again, were to say, we're guessing there are parts of your system you're really confident could scale towards that legacy, and others that maybe you're not so confident? Do you have any thoughts on those extremes towards a customer like the Postal Service?
Well, I definitely think that our future is going to be all about data. Data management, data processing, algorithms for data, manipulation. And so I would say that, focusing on those set of APIs or that part of the platform is likely to be something that we could evolve and go forward and support. Now, how we compute, how the underlying machines change, what languages we use. I think all that is sort of in flux, and there's no guarantees. If you push me on that, I would say that I would stick with the data APIs as something I could promise, and then I would not promise the other stuff, just as an effort. Other questions? Yeah. Yes.
You mentioned the different machines. Which clouds do you use?
Here, this is a local cluster, and I run Eucalyptus over that, and then I run AppScale over Eucalyptus. And Eucalyptus in this is not playing any kind of overhead role. Eucalyptus just does the deployment for me. Other questions? Yes. Is this AppScale what? Yes. 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 It works already. And we do it all. And it configures all the databases and all the. Yes. 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 As long as that hardware supports virtualization, right? It's, hardware-based virtualization or emulation. Yes, anything, yes. And we'll give you the images. We'll build the images for you. There's already an image in EC2 if you just want to grab it and try it. It's available. It's public. You just use it. You say, I want this image, and it'll deploy for you. And you use our tools to say how many right? You're paying for Amazon. So how many nodes do you want? Start with one or do four, and then the growing and shrinking. Say for Amazon, you would use something like right scale. We're not doing the automatic growing and shrinking right now. That's in-house, and that's research. Ah, good question. That doesn't. It doesn't. I like it that way because it allows me then to give me the portability to run over lots of different architectures. But you can just deploy it via apt-get if you guys use Linux. apt-get from our repository, it'll install on a 64-bit machine. I would do 64-bit. We supported 32 for a bit, but we'd probably get you going, but it's not great. I would use 64-bit. But yeah, you can just do apt-get and get it. But I can't then, it's not elastic, right? I can't grow and shrink. What's so nice about, I could grow and shrink, let's say, the servers. I could start up more servers. But what's really nice about having it be a virtual machine is that, let's say I filled up my virtual machine with like the application servers, the guys who run your front end. And now your database needs to grow. Well, I could start more virtual machines and grow your database and have it all work, right? So I need two levels of growing. Two levels of growing and shrinking. I need process level where I grow and shrink within a VM, and I need more VMs so I can grow and shrink across VMs. Okay, so that's why I do it. But there's nothing fundamentally that restricts you from installing on physical hardware, except you get no elasticity. Other things, yes? Yes. The HPC stuff? Yeah, right now what we're doing is stochastic simulations, so biochemical simulation systems, where you have a cell, and I'm not a scientist, okay, so I'm just going to just destroy this. You have a cell, it's really cool, you draw these meshes, and then you do adaptive mesh simulation-based processing. It's embarrassingly parallel. So they wanted a one-button way, they were just running on their clusters, and they run these little scripts to do that, and so we're working with them to both just to kind of steer the computation. So after a while, if you're doing a regular simulation, you may need randomness to, sort of find places to simulate. You can stop that simulation and start another one with the stochastic support, and then you can go back. So all that sort of adaptation is what we're working on now. One, it's nice because you can grow and shrink. Two, it's easy because it's embarrassingly parallel. I don't have to worry about communication so much. And three, it's a nice scientific app that lots of biologists use, biochemists use. So that's where I'm starting. Other than that, it's more like MapReduce problems, which again, bears thinking parallel. Yeah, so we have HDFS Hadoop running. And so it provides us with a distributed file system. So all the storage is then spread out and redundant. And then when a reduction happens, then we just say where we want the computation to take place, what node, and then it'll just be it's a server base. Client server based spawning of nodes, just like MapReduce. It's just MapReduce. All we're doing is configuring MapReduce and HDFS for you, and you have your database, and then those all work together. It's just the open source tool. I'm not doing any of that. I'm just using it and placing it originally, and then growing the number of nodes that participate. Okay, but everything else is Hadoop. Yes.
Another question. Let's say you were collaborating with folks, and they say we really like the Google App model, we really like this model. The only thing is we want to invert Google's model on hardware. So rather than sort of general purpose things, everything's going to have a lot of GPUs, a lot of FPGAs, a lot of cells, a lot of. How well does your mechanism support, especially if we want sort of awareness and advertisement services to be able to find these very particular heterogeneous sort of configurations?
Yeah.
So that our biochemical things will go, orders of magnitude faster.
Yes. Yes. In fact, we're writing a proposal right now just to research this. So the idea is, and that really has to do with this last piece of research, which is really work with the underlying infrastructure, because the infrastructure knows about it. So Amazon provides you with GPU service, and it says, here's the service, here's the GPU API that you can code against, and you just build a library and you write code against it. But then then you pay for that instance, that image. We need to be able to talk to the underlying, and if it's eucalyptus, it's free, right? So instead of paying. So we need to negotiate with the underlying infrastructure to say, hey, what resources do you have available first? And we can advertise that to the user or the simulation driver. But it's more manual, right, is what we're thinking at first. Sort of discovering that automatically is kind of tough. We can discover it automatically, but then we give it back to you, the scientist, let's say you are, and you say, oh, I want you to use the GPUs if they're available up to this many CPU hours. So I only get charged so much, or so I don't kill my machine, right? So we haven't really started that, but I think that that's the future, is that the hardware itself becomes serviceized.
And so the variation, you've, to my eyes, done a really impressive use of a lot of existing software tool sets.
That's right.
Bringing in. Now you want to say, what is the existing mechanism for describing that I need 50 terabytes of RAM and 48,000 GPUs? For that sort of hardware descriptor set, have you found any sort of open sourcey things you can build on?
Absolutely not. Absolutely not. And they're much more low level.
Rolling your own?
Yes, so we'll roll it alone, yes. And we'll just do it based on the actual stochastic simulation stuff first, just to do an interface with them so I understand exactly, so all the students kind of understand what they need, and then we can kind of evolve it. No, I don't know. And if you have suggestions, I'd love to hear it. I don't know. I think this is really interesting stuff, though. Yes. Exactly. That's another interesting question. GPU hours, CPU hours, exactly. And there might be, how are you going to know, right? How are you going to know before you start executing? So what we want to do, because we can interface to the underlying infrastructure, therefore the cost models, you can say, I don't want to spend more than $50 or $100. And we can just use the resources, the most maximum resources that we can, until we run out of money. Or you say, I only want, or I want to only, and CPU hours comes from, that's how you cut it off, right? Amazon rounds around to a CPU hour, but it's arbitrary. How about those cost models? If you're interested in that, we're not working on that either, and someone should, right? I have people all the time, I go give this talks like these all the time, and they're saying, all right, if I executed AppScale in Amazon and I ran 14 Google App Engine apps, is that cheaper or more expensive than if I ran those Google apps in Google? I have no idea. And you know what? Neither does Google and Amazon. If you go and you pay for Google or you pay for Amazon, that the price actually for some of those resources varies depending on load. How fair is that? You guys are running with other people, and therefore you're going to be charged more, right? If you run on resources that have fewer other people using those resources, you could charge less. I know, it's true. But the cost models is a great research question and a great research problem, and no one knows. How are you going to charge for these things? Nobody knows. They charge, but they have no sort of foundation or understanding behind it. So we thought what we would do is you could run your stuff in App Engine or AppScale, and then we could predict what the cost would be in Google. Turns out it's impossible, because the cost depends on how many other people are running in Google. So it's just hard. But anyway, it's really cool, and Sure, I can do that, but I can't. But the difference between what I predict will be your cost, or if I charge you. Yes. The problem is, but the thing was, if I was running my app in Google at this moment, and I could actually do, so what we tried to do, so Google gives us a time series of their load. So we go and sample that and say, okay, if you ran your program at this exact time, here's what your cost would be. But people don't want to, so we would. Yeah. Yes. Or then it says 25, right? I mean, yeah. See how accurate those are. But yes, we could try that. I think it's a great idea, and someone needs to work on it. I think it's a great problem, and that we have a whole cost interface for people to play around with this. I just need more students. All right. Any other questions? Again, thank you so much for coming. I really enjoyed talking with you.